Hello, everyone. Welcome back. So today we want to talk about velocity and acceleration, basically how they're related to position and also how they're related in terms of derivatives. So our goal is understanding the relationship between velocity, speed, and acceleration, which we'll talk about here in just a moment, and then also look at some application problems involving those three. So first off, let's talk about these three: velocity, speed, and acceleration. So if an object is moving in a path, some doesn't have to be a straight line, could be a curved path. Whereas position, we call that s. It could be in feet, meters, whatever given as a function of time, and time can be in seconds, minutes, hours, whatever as well. It's given by this function. In this case, it's just this function of time. It's a function of time only. S equals f of t. If that's true, if we can define its position just as a function of time like this, then the velocity of the object is given by the first derivative with respect to time. If we take the derivative, that's our velocity we call v, and that's the derivative of s with respect to time. We write it as it's f prime of t. So our position of function position is given by our function f, or as ds dt. So that's the velocity. It's the first derivative of the position with respect to time. This thing about hopefully makes sense. Velocity is usually given in distance divided by time. So if s is in distance, and you can see that in the units, if s is in distance, then the denominator we have time. We have position in the numerator, distance or time the denominator, or distance the numerator rather, and time the denominator. That gives us distance over time, which is speed or velocity. Now, specifically, speed then is the absolute value of velocity. In general, I'll go ahead and mention that velocity and also acceleration, which we'll talk about in a moment, are in general are vectors. They have both speed, they have both a magnitude. Remember, from vectors, a vector has a magnitude and has a direction. That's true of velocity and acceleration. They have magnitudes, how large they are. They also have some direction. Okay, where speed is just the absolute value of velocity. Just like when you're driving down the road, what's your speed? You only give them one number. It just has magnitude. Give them 50 miles an hour, 60 miles an hour, whatever. But velocity, you have to have both speed and a direction. So for airplanes and ships, since they don't move on highways, they have to consider both their velocity. They have to think about not only how fast they're going, what direction they're going in. So an airplane, it might be going 200 miles an hour in a certain specific direction, maybe due east or something like that, or for a ship, similarly. And finally, acceleration, we take the derivative of velocity, that's acceleration. So velocity is how fast position changes with respect to time. Acceleration is how fast the velocity changes with respect to time. Or it's basically the first derivative of velocity or the second derivative of position. And that's what the acceleration is. And of course, velocity, speed, and acceleration are very important in physics and engineering and other areas. So remember that velocity and acceleration are vectors. They have magnitude and direction, but speed it just says magnitude only. So let's practice these ideas, look at some examples. So let's come over here to the right. Let's look at this one. This is one actually out of a textbook. So it says, suppose a stone is thrown vertically upward from the edge of a cliff on Earth with an initial velocity of 19.6 meters per second. That's how fast you're throwing it up. And from a height of 24.5 meters above the ground. And then it gives the height in meters of the stone above the ground t seconds after it's thrown is given by this equation. Let's draw a kind of really basic picture of what this looks like. So you have maybe it's kind of a platform, or maybe it's part of the ground or cliff or something like that. So basically you throw this stone up in the air, then it comes back down and hits right there. Now this position right here, where time equals 0, the starting time, okay, the position, as it says, is going to be initial height is going to be 24.5 meters, okay, above the ground. Now, its initial velocity, the velocity right here, is going to be how fast you're throwing it, 19.6 meters per second. Okay. Now, what's going to happen, of course, is you throw it upwards, it'll go up, and because of acceleration due to gravity, in a downward direction like this, then basically that acceleration due to gravity is going to cause it to lose velocity, lose speed. So it finally reaches some place where the speed is 0, then it's going to come back down. Okay, that's basically what's happening. Now it says this curve in respect to time can be given by this. Now be careful. This drawing I'm showing here is kind of respect to the space position, but the curve with respect to time is given by this. Well, let's actually plot this with Desmos. Let me write it down first. I have to keep going back and forth. Let's go over to Desmos. Let's actually plot this and see what it looks like. Okay, so y equals, which is in terms of x, but still think of x as our t. So y equals negative 4.9 x squared plus 19.6 x plus 24.5. Okay, now to look at our graph, we need to zoom out a bit. Now, if you notice, of course, remember this is a quadratic function. It goes on forever in both directions. Since our x-axis is time, we only care about positive time. In fact, let me actually change our scale here. So remember, this is something you can do with Desmos. Let's go to our settings. So let's see, where does it end right here? So actually, this point right here, looks like about 5 seconds is actually about when it hits the ground. We'll talk about that in a moment. So let's change our scale. So the y-axis, let's see, goes up to about 45 or so. So x-axis, let's go from 0. Now let's actually go a bit negative so we can see the whole thing better. So let's go back to -1 to -1 to 5. And then in y, let's go from 0. So let's go like -1 again, maybe -5 to maybe 50. How that looks. Let's actually make this 5.1 so we can see everything a bit better. Maybe 5 point, let's do it 6. There we go. Okay. Now, so I did that to make it a little easier to see. So once again, what we're seeing is a position with respect to time. Okay. So our initial position, as we said, about 24.5 meters. All right. Let's actually label that one. So 0 at 0 seconds and 24.5. That's our starting point. So time equals 0. Okay. Now, where it hits the ground right here, and actually this is, let's label that 0.50. Why is that point important? Well, because when is it position 0, this is when it hits the ground right here. Okay. The ground is at position 0. And then actually, so we're interested in finding this point right here, highest point. We'll talk about that in a moment. That's our basic graph. Once again, this is in time, even though throwing a stone or throwing anything object often follows kind of a parabolic path like that, but still we're talking about in time. Yeah. So right here, I should have mentioned as well, here, S is equal to 0 right there. Okay. Now, it says the first thing we want to do is determine part A, determine velocity of the stone after t seconds. So basically, the velocity is just going to be the derivative with respect to time. Okay, so we know how to find a derivative. So it's going to be negative derivative of this, negative 4.9 times the derivative of t squared is 2t. Okay, plus the derivative of 19.6t, just plus 19.6. And then, of course, derivative of the constant is 0. And so let's make that look a little bit better. And so it's going to be negative 4.9 times 2 is negative 9.8, and then t plus 19.6. So this is our velocity. Okay, so this gives us then the velocity of our stone as it goes, as it continues on our path. Okay, so when does the stone reach its highest point? Now we can also get that from the graph from Desmos. But let's think about this. So basically, we said it's going to go up here and has the initial velocity of 19.6 meters per second. Right here at the top is where the velocity is the minimum. Okay. Highest point is where it's the minimum. All right. Now, the velocity, since it's position, the velocity is the minimum right here. Actually, I'm sorry. Let's go back up. No, that's not true. That's where the, sorry, I'm saying the wrong thing. It's not the minimum, but that's where I was thinking what I'm saying. All right. So at this point right here, what's happening is that, no, that's true. Actually, the velocity right there is zero. So right here at this point, the top, the velocity is zero. That's what I meant to say, not the minimum. Okay. The velocity is zero. So we can actually find that from this. Okay. So part B, just solve. This is V, or V of t is equal to zero. Okay, and so we're going to have negative 9.8 t plus 19.6 is equal to 0. All right, and so we have negative 9.8 t is equal to just negative 19.6. So to solve this, then t, of course, use your calculator. It's something you want to try and do in your head, unless you have to. And let's see if we divide that. So 19.6, it's going to be positive. Okay, oh, that's actually going to be evenly. It's going to be 2. Okay. Now, think about a couple things. Now here, remember, this is time, the time when the velocity is 0. All right. Also, this is 2 what? Remember, we're talking about in seconds. So meters per second. So this is in 2 seconds. Okay. So 2 seconds, that should be the highest point. Let's go back to our graph and see if that appears to be true. Okay. I believe, yeah. So 2 seconds, that appears to be the highest point. This x, but this is essentially our t coordinate. Let's label that point 2 and 44.1. And that's our highest point, once again, at 2 seconds, which we expected. Okay, that's our maximum height. Now, that was part B. Part C, what's the height of the stone at the highest point? And basically, once we know the time in which that occurs, we just plug that back into our formula. And I won't go through the details. You can do that on your own. Of course, you can see it on the graph. That's going to be S of 2 and that said it was about 44.1. And our units here then are meters. Okay, that's where height is given in 44.1 meters. All right. We saw that on the graph. Part D. When does the stone strike the ground? Okay. Now this, you really need more to find out basically from the function itself. Unfortunately, the velocity isn't really going to tell us that much as much. It is going to be kind of a maximum. It is essentially going to be the highest in terms of, or actually maximum speed. The fastest speed will be right here, okay, when it hits the ground. But that's harder to tell, basically, because we don't know for certain, especially without the graph, which we saw is about 5 seconds. But without the graph, it'd be hard to tell that. So you know exactly when its fastest speed occurs. Because as far as a function, this course goes on forever. But here, we're talking about where it hits the ground. So basically, the best thing to do there, that is going to be, you have to solve S of t, take your function, set equal to 0, is where the ground is height equals 0. So we said in our graph. The ground, and this is the ground, height equals 0. And if you do that, let's go back to our graph. That is basically after 5 seconds. So if you plug that, solve that, which would be 7 quadratic equation, but basically that t would be 5 seconds. That's when it hits the ground. Okay. Now, with what velocities the stones strike the ground? All right. So our E, so what you want to do now that we have the time hits the ground, we plug that into our velocity equation right here. And so that's going to be V of 5, and that's going to be negative 9.8 times 5 plus 19.6. And let's calculate that. So use your calculator. And so that's going to be negative 29.4. It should be a 4 meters per second. Remember, our velocity is in meters per second. Okay, when it hits the ground. That's how fast it's going. Okay, if you notice, that's faster than the velocity which we threw it up, which is 19.6. Okay, and it kind of makes sense. We threw it up from a greater height, and so it's going. So basically, right here, when you're at the same height, it should be the same velocity as we threw it, but since it's had more time to accelerate, that happens. Okay, that's when it hits the ground. Okay, and then part F. What intervals is the speed increasing? Okay, here it kind of depends on what you mean by increasing. So basically, our speed. Oh, okay, well then, sorry, the speed is increasing. The speed then. So let's actually go and take a look at our thing about the velocity. The velocity, depending on whether you mean going up or down, is increasing. But let's look at the velocity. So let's go back here. So negative 9.8. Let's actually graph the velocity as well. So y equals negative 9.8x plus 19.6. Okay, so let's kind of zoom out a bit so we can see that. But basically, this is our graph of our speed. Okay, notice here's our initial speed right here. Okay, now the reason why this is negative below is what's happening. Okay, right here, okay, so as we throw it up, remember velocity has direction, and velocity is a vector, so it's magnitude and direction. So this gives both the magnitude and direction. So right here, we're throwing it up, and basically we're thinking of an upward direction as being positive. So I'm throwing it up. So it has upward speed. It says positive speed. That's why this is above the x-axis. It has positive speed, but it's slowing down, right? So although speed is still positive as it's going up, it's reducing. You can slower until this point right here. Okay. And then the magnitude of the velocity increases, but since now the ball is now going down, the speed, our direction is now negative since we're going downward, but our magnitude increases or our speed increases here. Okay, so here our speed is decreasing since it's going downward. Although our direction is up, it's positive. Here our direction is negative, it's downward, but our speed is increasing. Okay, and so it stops decreasing then at 5 seconds. Because that's when the graph hits the ground at 5 seconds. So basically, from 2 to 5 seconds, our speed is increasing. From 2 seconds to 5 seconds, or as an interval, right, that is from 2 to 5. Okay, that's when it's increasing. The speed is increasing when the speed is the magnitude. Okay, also let's do one more thing. It doesn't actually ask us to do this. Let's let's find the acceleration. Okay, so for the acceleration then, a, called also a of t, also be a function, is going to be the derivative of the velocity. Let's go back and look at our velocity. Our velocity function is this. Now I should probably make this as a function of time. Okay, take the derivative of this. This part, of course, is just negative 9.8. Derivative of this part is 0, so our acceleration is negative 9.8. Okay, that's a constant. Now, also our units there are actually, since velocity is given in meters per second, then this is also divided by seconds again, meters per second, or meters per second squared. That's often how you see your velocity. You probably had in physics class or something to discuss that. This is 9-9.8 meters per second squared. Okay, so this is meters per second per second. And once again, it's negative because this is going downward. So acceleration, we said, is pointed downward. Okay, it's consistent with the velocity. So the velocity is also downward when it's going in the downward direction. Okay, so that are just some of the basic ideas. Let's take a look at our next problem. This is kind of interesting. It's about tree growth. So it's a little bit different from just the usual acceleration and velocity, although the principles still apply. All right, this one says, let B represent the base diameter of a conifer tree, let H represent the height of the tree. Where B is measured in centimeters, H is measured in meters. Assume the height is related to the base diameter by this function. Okay, so the idea here is we have a tree. Okay, let's see if I can kind of draw a basic tree here. Conifer tree. So imagine it looks something like this. You get the idea. Okay, down here at the base, let's say it's a circle. Okay, so this is our height, H, given in meters. And our base, let's just draw a picture of the base. Here's our base, which is a circle. And its diameter, the diameter is a distance, the diameter is all the way across the diameter. Sometimes I have trouble writing how I want to on this. It's also the diameter all the way across, the radius. It also works the same way. This diameter is in centimeters. Okay, so the height's in meters, diameter in centimeters. All right. What it says then is basically the height is really the base diameter by this function. Okay. What this tells us is how basically how tall we expect this tree to be based on its base diameter, how big it is across at the bottom. Okay. And basically they can often get ideas or get functions like this a lot of times through just collecting data. So if you ever talk about how to curve fit data, so basically you have a bunch of data for a bunch of different trees for this base diameter and height, and then basically they use something like Microsoft Excel and basically with an equation like this to express those, relate those two. So first is graph the function. Let's graph the height function. Let's do that. There's something to write it down, so we have to keep on coming back to this. 6.7 plus. Okay, let's go back and go back to Desmos. That might be better just open up another Desmos window. Okay, well, it's going to do it in terms of y and x, but same thing. So 5.67 plus 0.7x plus 0.0067x squared. Okay, now I'm going to need to zoom out a bit. Okay, now I don't think it told us exactly what the limits would probably be. But basically what we have is a very kind of large wide parabola, as you can see. Okay, so remember our x-axis is in centimeters, and this is in meters. So this is our base diameter in centimeters and our height in meters. Okay, so that's what the graph looks like. So it just shows kind of this parabola and this kind of a quadratic increase like that, the x squared. Okay, so that's the graph. Actually, 5.67 is actually our y-intercept, although I'm not sure what the problem does actually tell us what that means for the problem, why that is the y-intercept, but that's it. So graph looks something like this. So 5.67. All right, this is the height in meters, and this is the base diameter in centimeters. It looks something like that. Okay, now graph the height function. So what this says is the base diameter, it increases in a quadratic way. So as the base diameter increases, then the height actually gets a lot, the bigger the base is, the height actually increases quadratically from that. Okay, then part B, this is part A. Part B, plot and interpret the meaning of dH dB. Okay, so that's going to be the derivative. So part B, dH dB, let's take the derivative of this. Okay, so take the derivative of this function. All right, so of course the derivative of that part is a constant that's 0. This is just part's going to be 0.07. Also write as h prime b. So 0.6 to 0.7 plus, then the derivative of this part, so it's going to be 2 times 0.0067 x b. So the constant out front, 0.0067 times 2b. Okay, and then just multiply that out. And so this is going to be 0.7 plus 0.0134 b. Okay, now this is dH dB. Okay, this tells us, all right, so that's what that is. Now, I think it wants to plot it and interpret it. Plot and interpret this meaning. Okay, so what does this mean? All right, so remember, this essentially is like a speed. Okay, it's a first derivative. Now, it's not truly a speed. It's not, since we're talking about not in terms of time, but basically this tells us, this is telling us, is remember what a derivative tells us. It tells us, you think of this either instantaneous rate of change. This gives us instantaneous of change of the height of h for some value of b, the base diameter. Okay. And one also thing that tells us that, and also say it tells us, these bullet points, it tells us how fast h increases as the base diameter increases. Okay, and if we plot that, let's plot that on the same axis. So let's go back to Desmos. Let's plot on the same set of axes. So y equals 0.7 plus 0.0134 x. And you see it increases pretty slowly. So let's kind of zoom in a bit until it's not quite a flat line, but it's fairly flat. Of course, your slope thing, but our slope is pretty small. It basically tells us how it increases. So basically it says it's not a very fast increase. Okay, but basically, since it's all positive above the x-axis, that means it's a positive growth. So basically positive. So as the base diameter increases, the height increases. And it tells us that basically it's a slow change. So basically the difference in how fast it grows, say at 10 centimeters versus 20 centimeters isn't actually all that fast. It doesn't change that rapidly. It is faster. Okay. Let's look at one more problem. Okay. Have a thought. Probably kind of a thought question. So it says a woman is attached to a bungee cord, jumps to the bridge, is 30 meters above a river. 5 meters above the river, t seconds after the jump is given by this function. Okay. So basically it says you want to determine her velocity. And then also kind of graph it to understand what the graph looks like. So first off, let's graph this. Let me write it down first. So 15. So let's go back to Desmos. I think once again, we'll just open up a new Desmos window. Okay, so the graph, I'll also use add y and x again. 15 plus 1 times 1 plus e raised to the negative x times cosine of x. Okay, now we need to zoom out of it. That's kind of looks strange. And basically, of course, needs to focus on what's going on in the positive side of things. Okay, let's zoom in a bit. And once again, it says basically right here at 30. So we're starting at 30. Okay, and then basically our graph shows her she's falling. All right, down through here, and then of course it bounces up. And this function using may not be all that realistic. It's like it stops, kind of stops too soon. But still, this is just the model we're using. All right, that's her path. So her position, back to time. She gets down here, her minimum height, and she bounces back up and kind of levels off. Now, you can't see it is kind of oscillating here, and that's kind of hard to see. Okay. But our first question is actually want to find her velocity. Okay, so remember this is the position. Velocity, part A, is we need to find the derivative. So velocity is going to be y prime of t. Okay. And so actually I'm going to write this kind of distribute the 15. So it's going to be 15. If I distribute the 15 here, I have a 15 here and a 15 here. Okay. In fact, let me just do that. Let me back up a second. So start with y of t. I'm going to write this way. It's easier to take the derivative. 15 plus 15 times e to the negative t times the cosine of t. Okay. Now, so velocity is going to be y prime of t. Of course, this part is going to be 0, constant. Here we're going to have 15. Now here what we have to use is actually have to use the product rule. Since we have a product of two functions of t, so the derivative of e to the negative t, that's basically essentially a chain rule issue. Okay, so the derivative of e to the negative t, e did something, of course, it is first e to the something, e to the negative t. Then using the chain rule, the derivative of negative t is negative 1 times the cosine of t. Okay, then plus the first function by itself, e to the negative t, and then the derivative of cosine is going to be negative sine of t. We have a parentheses there, so that's our function. Let's clean up a bit, make it look a bit better. So the velocity, which is a function of time, okay, is going to be back up here. So we're going to have, notice we have a negative in both cases, a negative here and a negative here. Let's bring that out. Negative 15 times, I can also bring out e to the negative t. Let's have e to the negative t in both. And so this is going to be e to the negative t. And what I have left on the inside is cosine of t plus sine of t. Okay, double check that. So we have a negative here and a negative here. 15 was out front. And then I can also factor out an e to the negative t in both. What I have left in is the cosine here and the sine. Once this is positive, you distribute the negative back through, you get that. Okay, that's my velocity. Now, so basically I want to find the velocity at t equals 1 and t equals 3. So v of 1 and then v of 3. What I'm going to do is, of course, you do this on your calculator, but I'm going to graph this. I just going to think it's going to be a little bit easier to do it. So maybe I'm actually just going to graph it. Then we'll, oops. Actually, it should be 1 and 3. So the velocity at 1 second, the velocity at 3 seconds. Let's go back and graph that. Back to Desmos, and we'll see what we get. Okay. So y equals negative 15 times e raised to the negative x times, in parentheses, cosine of t plus sine of t. Nope, x, sorry, x. using X. Okay, so way down here is this function. So let's zoom in on it. Where this is our velocity, how the velocity changes. And if you kind of match these up, let's zoom out just a bit if we can, so you can see both ideas. Our position here, the red is our position. So we're starting out 30 meters. And of course, being a bungee jump, our position is decreasing, but also should be accelerating, right? We should be accelerating some that's going to start to slow down, all right? And this shows us kind of well, actually our fastest speed is probably going to be at the top. And then as the cord kind of starts to stretch out, we slow down, all right? Then right here is where we reach our zero speed and then start to increase again, okay? And here, once again, we're thinking about down as being negative and up being positive. So we see that in our velocity. Right here, our velocity has the largest magnitude right here when we're beginning. Okay, it's still negative since we're going downward. Okay, but the velocity is decreasing as it should as the cord stretches. Then right here at the same point is basically where we have our zero, actually to this point right here. So we have our zero velocity. And then the velocity begins to increase a bit as we go back up and then we come back down. Okay, now, once again, let's plug in. So at 1, negative 7.625. So 1 is negative 7.625. And that's probably in, I believe it's in there's a river. And the river T seconds after the jump, right? So if our position is in meters, our times in seconds, this is going to be in meters per second. Okay, and once again, it's still negative because we're going in a downward direction. Now let's go back and get at 3 seconds. Okay. At 3 seconds, we're at 0.634. That's positive, 0.634. Meters per second. So that's after we've hit our lowest point, and then we're coming back up, then our speed is increasing at that point. Okay. Now, that's part A. All right, so the first 10 seconds, one was moving upward, one was moving downward. Okay. And maximum upward velocity. Okay, so in the first 10 seconds, okay, so the first 10 seconds, we want to stop right here. So when you're moving upward and when you're moving downward, you can tell that kind of from the graph here, position graph, but also you can kind of tell it from this. So we want to get 2 particulars, see if I can zoom in a bit more. This graph is actually kind of oscillating, what's really hard to see. Okay, our oscillations are really small. Okay, so basically from here, I might even write anything down when it's talking about it. So basically here, you notice so basically whether we're above this the velocity graph, whether you're above or below the x-axis can tell you whether you're increasing or decreasing in speed. Okay, so if you're below the x-axis, you're decreasing. And wait, hang on, this is velocity or speed? So I'm gonna get these backwards. No, when she's moving upward or downward in the first 10 seconds. Okay, yeah, upward or downward. So that's easier to say, right? So upward or downward. Okay, basically you can tell that by whether this velocity graph is above or below the x-axis. So wherever below the x-axis, you're moving downward. When you're above the x-axis, you're moving upward. Okay, so yeah, so basically we see the graph. So from about 0 to 3, 5, or 4, and once again that's in radians. That'd also be time. So basically here, everywhere from 0 to here, we're moving downward. Okay, now here we're above the x-axis where the velocity is positive. We're obviously moving upward. They move downward here again, and then as you can see, it's really hard to see, but you get the idea. Okay, so wherever your velocity graph is above the x-axis, you're moving upward. So that's where we define upward velocity. Then moving below the x-axis, you're moving downward. Okay. And what was the last part? using graphing utility to estimate the maximum upward velocity. So basically the maximum upward velocity, let's go back to our graph, okay, should be the highest point. So this is our velocity graph, should be the highest point on this velocity graph. The maximum upward velocity, once again, upward means we're above the x-axis on our velocity graph, and the highest point, in fact, Desmos kind of shows you where the maximum is, but it's right here, okay? So this is pi, about 3.14 seconds after jump, and then that's a time when we reach the maximum velocity, upward velocity, and then the maximum upward velocity is about 0.648 meters per second. Okay. Now you can also find that by taking this, your velocity equation, set equal to 0 and solve, if you can actually solve that. Perhaps some can be difficult. That's why it's useful to be able to graph it. That's the idea. Okay, let's review what we've learned. So basically, we learned the relationship between velocity, speed, and acceleration. So remember, we have a position given by some function, it's just a function of time for now in one dimension. S is a function of time. You take the first derivative of your position, that gives you your velocity. The absolute value of the velocity is speed. And then you can take the derivative of velocity, which is the second derivative of position, that gives you the acceleration. Remember, in general, velocity and acceleration are vector quantities. You need both a magnitude and a direction. And then speed is just a scalar. You need only magnitude. Thank you. Have a good day.